Already we have an idea regarding the classification of radiation sources, and we are generally classifying radiations as 4 types: free electrons, heavy charged particles, electromagnetic radiation, and then neutrons. In this you have free electrons. Then heavy charged particle means there you have alpha particles, protons, then heavy nuclei formed from nuclear reactions, etc. And in electromagnetic radiation you have gamma radiations as well as X-rays, and last one is neutrons. And in this free electrons and heavy charged particles are grouped as charged particulate radiation. That means they are particles. And uncharged radiations are electromagnetic radiation and neutrons. This is one way of classification. Or you can classify radiations as ionizing radiations and non-ionizing radiation, or as soft and hard, etc. And now what we are doing is how you can produce these charged radiation sources. So we will discuss them one by one, and we will start with the fast electron sources or electron sources. And we have 3 common methods for producing fast electrons. They are beta decay, internal conversion, and Auger electrons. And we can start with the beta decay, and this is your normal beta decay reaction, familiar to you. You have a parent nucleus with X, Z atomic number, Z and A is the mass number. When it is emitting a beta particle, that means beta minus or electron, its atomic number will be increased by 1 and the mass number remains the same. So this is the electron beta. Also, this is known to you. It is there is an anti-neutrino also emitted in the reaction. And normally, beta decay is due to the decay of a neutron, that is given here. This is also known to you. And when a beta is emitted, normally that you have a parent nucleus, daughter nucleus, beta, antineutrino plus some energy that you are calling as the Q value. And this energy will be normally shared by the products. That is the general case. And if you are initially assuming that your parent nucleus is at rest in order to conserve the low momentum, the particles will be, the products will be emitted in opposite directions. These things are known to us. And it is found that normally the heavier particles like nucleus will almost remain stationary, or they will not be in motion. That means this energy is mostly shared by the beta particles and antineutron, that we will discuss later. And most beta decays results in an excited state of product nucleus. Due to the subsequent de-excitation, gamma rays are also emitted together with the beta particles in many common sources. This is also known to us. In most beta and alpha decay, you can see that a beta or alpha is followed by a gamma. This we have just mentioned. Energy of the recoil nucleus is 0. And the decay energy is shared between the beta particles and the neutrino. The beta particles thus appears with an energy that varies from 0 to a maximum value. That means if the energy is not equally shared among beta and neutrino, sometimes beta will get more energy and sometimes neutrino. That means the energy of beta is not constant. It varies. If the whole energy is carried away with the neutrino, beta particles are just emitted. That means with zero kinetic energy, or the electrons will have zero energy, that you will see. Or it can have a maximum energy with the energy given to neutrino is 0. So you can see that normally if this E beta is the energy of beta particles, and this in y-axis you have the number emitted. You can see that this is the observed spectrum in this blue color. You can see that this is with zero energy. So this is the maximum value or maximum number you are getting for a particular energy. Then it again decreases, and this is the maximum value, and that maximum value will be the Q value of the reaction. So that energy is the maximum energy that a beta can, and above this you have no beta particles. That is why this written as not observed and this as observed. So this is known as the end point energy of beta, and this will be discussed in detail in your beta decay chapter. And the next one is internal conversion. An excited nuclear state is formed by a preceding process. That means, preceding means which is already undergone. That means due to some reaction, your nuclear state is at an excited state. Normally you will return it with if X is a nucleus, X star, that means it is in an excited state. So normally what happens, all nuclei will try to go to the lower state by emitting the difference in energy, and the nuclear excitation energy, that means nucleus will be coming from the upper energy state to the lower energy stage, and that difference in energy it will emit, and this emitted energy will be directly transferred to one of the orbital electrons. And that orbital electron is bound to the nucleus, and if it is getting some energy, it can excite or it can eject from the atom. So that it will be ionized, or it will be equal to the ionization energy, or it will be equal to the, if that electron is getting an energy greater than the binding energy of that electron can escape from the atom. So thus you are getting an electron, or it is a source of electron, and this is known as internal conversion. That means your energy is internally converted as, or internally given to the electron, and it is ejected. That energy is not coming outside the atom. That is why it is known by the term internal conversion. For the internal conversion, you can write this expression as E of electron, EE, equal to E excitation minus EB. Here this E excitation is the excitation energy of the nucleus. EB is the binding energy of the electron. So this is the kinetic energy with your electron is emitted. And this is a pictorial representation. This is a normally common example. Here you have mercury, Hg. By a beta emission, it is given to this TL. And this is in the excited stage. There you can see the star. So this is in the excited stage. And it can go down to the de-excited stage by emitting an energy or emitting a gamma. This is the common reaction we are getting. So if it is emitting a gamma, which means that gamma is emitted out of the atom. You can see that. But in some cases, this is the case. This energy is not emitted as gamma to outside, but that energy is given to one of the electrons in the K shell. For example, we are considering K shell. So that electron is emitted, and this is internal conversion, and this is the normal gamma emission. And this internal conversion can be either from K shell, or that energy can be given to one of the L shell electrons. All is possible. So this type of emitted electrons are due to internal conversion. And the conversion electron can originate from any one of different electron shells within the atom. Thus, a single nuclear excitation level generally leads to several groups of electrons with the different energies. We have already mentioned that the electrons are emitted with the energy, which is the difference in energy of the excited state and the binding energy. The binding energy is different in different shells. So when binding energy is decreased, it will be emitted with more energy. And you can see that the K shell electrons are emitted with least energy because the binding energy of the innermost shells are more. So K shells are, the electrons from the K shells are emitted with low energy, and it is going on increasing to L, M, N, etc. And here for the L, normally you are giving some 2 peaks because in the second shell, the L shell, it can have 3 subshells, and this first, second, third, etc. are the subshells of a particular shell. The spectrum of the internal conversion may be superimposed on a continuum consisting of beta spectrum of the parent nucleus that leads to the excited stage. We have already shown this. Here you have a beta spectrum, and after this beta spectrum you are getting an internal conversion. So the energy spectrum of electrons generated from beta spectrum and internal conversion, they superimpose like this. This we have already drawn, and this is the beta, and on that our internal conversion electrons also merge. So like this. And this is the third method, Auger electrons. Or sometimes you are familiar with the term Auger effect. That's an effect discovered by a scientist named Auger. That is why it is known as Auger electrons. And Auger electrons are the analogue of internal conversion. We have just mentioned that internal conversion electrons are emitting from an atom by taking energy from the nucleus. That means from nucleus you are getting some energy. And here excitation energy originates in the atom. In internal conversion, excitation energy is from the nucleus, and in Auger electrons it is from the atom. In internal conversion, electron ejection is due to the nuclear excitation energy. So here also a preceding process such as electron capture may leave the atom with a vacancy in the normally complete electron shell. Then the atom will be in an excited state. So an atom is getting some energy and electrons are knocked out or some electrons are removed. So your atom is at a higher energy state. Now what happens? That atom it can reduce its energy, and there are two possibilities for that. This is the normal one. The first one is a normal one we are familiar with. That means the vacancy is filled by an electron. That means one of the innermost electron is removed. So an electron from the outside shell or outside electronic level can go into the inner level. That is, the vacancy is filled by an electron from one of the outer shells with an emission of characteristic X-ray photon. That difference in energy is emitted, and here you can see that energy is, if it is a heavier atom, that energy will be very large, and the larger energy will be in the X-ray region. So it is emitted with an X-ray photon. This is one method, and this method is not producing any electrons, but the second one is important to us. This is the method in which Auger electrons are produced. The excitation energy of the atom is directly transferred to one of the outer electrons and causing it to eject from the atom. This electron is called the Auger electron, and this effect was termed as the Auger effect. And how this happens, you can see. We have a picture. A high-speed electron knocks out one electron. So you can see that this electron is moving from here and you have a vacancy. And now what happens? There are two possibilities. This is the first possibility we have discussed. This is the vacancy, and to this vacancy an electron from the higher energy level is filling that vacancy, and that difference in energy is emitted as photon emission, that means X-ray emission. And this is the second one. Here you have the vacancy and you have this is the electron which was knocked out from the inner one. So what happens to that excess energy? That energy is given to one of the outermost electrons and it is ejected. This is known as the Auger electron. So these are the two possible methods. Now you can ask a question. In a particular reaction, which is possible, X-ray emission or Auger electron? That we can explain in the next slide. This Auger electrons appear with an energy given by the difference between the original atomic excitation energy and the binding energy of the electron. This is an expression similar to that we got in the internal conversion. And the energy of Auger electron is relatively low compared with the beta particles or conversion electrons. That is also known to us. The energy levels in the atomic states are much lower than that in the nuclear region. These beta particles, nuclear origin, and also the conversion electrons are due to the energy from nuclear states. And normally atoms with Z less than 30 tend to give Auger electrons. With Z greater than 30, normally you are getting the characteristic X-ray emission. And that's all.